Hello everyone, welcome back to another video. In this video, we'll learn about B-trees. We'll learn everything about it, like how it works, where is it used, how it is used, and all the operations that are possible on a B-tree. If you want to go by the definition, it is a specialized MV tree designed to optimize data access, especially on disk-based storage systems. So this definition might not be very clear to you at the moment. We'll get back to it. So before we dive into B-trees, let's take a quick recall at binary search trees. So in binary search trees, if you remember, binary means two. Each node has a maximum of two children, and let's say this is 50. All the left subtrees is smaller than this, so let's make it 20. All the right is greater than 50, let's make it 80. Now if we extend this further, it has to be less than 20, it will be 10. Now when we insert on the right side, it will be greater than 20, but at the same time it has to be less than 50 because it is lying on the left side of it. So let's make it 40. Okay. Similarly, less than 80, but greater than 50 because it is on the right hand side of 50. So one such number can be 60 and greater than 80, one such number can be 100. Let's take one more example, extending it so that it is clearer. Less than 10, we can make it 5. Greater than 10, but less than 20. Okay, because it is on the left hand side of 20, it will be 50. Similarly, 80 and 60 is there. So it has to be less than 60, but it has to be greater than 50 because it is on the right hand side of 50. So one such number can be 55, right? And on the right hand side of 50, it should be greater than 60, but it should be less than 80 because it is on the left hand side of the 80. Uh, One such number can be 70. So I hope this was clear to you. This is what binary search trees are and how they insert the data. This is binary search tree. Now, what is the problem with this? A database will have millions of records, right? And when you are supposed to search a record, as the number of entries grows, the height of this tree will grow. And when you try to insert or I mean search for a key, the time it takes is log of n, right? Now you start with here, then you move here, then you move here, and then you move here, and so on. So as the number of records in the tree increase, the number of nodes will increase, and because of that, the time it takes to find that node will increase, right? So this is the exact problem that is solved by B trees. Let's see what are B trees. So one main point, or the main differentiator, the first and foremost differentiator, each node can have more than one keys. So in binary search tree, we saw that each node has only one key. But in case of B trees, each node can have more than one key, and each key is sorted. So whenever you insert a key, it will automatically be sorted. It will always be stored in a sorted way. Okay. So this is a of node of a tree. Great. Now there are some formulas, some properties of B trees that we should understand before we can dive deeper into it. So I have a document pasted. Let me quickly grab that. Great. What are the key properties? First, before that, what is an order of a B tree? The order is the maximum number of children a node can have. So in this case, let's come back to our previous example. We have a node. It has 5, 10, 20, and 30. So similar to B trees, all the child nodes are also sorted. So for everything that is less than 5, it will come here. For everything between 5 and 10, another node will be formed. For anything between 10 and 20, another node is formed. Between 20 to 30, another node is formed. And greater than 30, another node is formed. So if you want to see, this is greater than 30, this is less than 5, this is between 5 and 10, between 10 and 20, and between 20 to 30. There is no other possibility, right? We have covered all the possibility here. So an order is the maximum number of children a node can have. So this is 1, 1, 2, 3, 4, and 5. So the order of this tree is equal to M. Order is represented by M. This is order. Okay. So now let's get back to the properties. So maximum children per node, we already saw it is M. There will be minimum number of children per node as well. So there is a formula for that, that is m by 2. So if m is equal to 5, m by 2 uh, ceil of that will be 3. Okay, this is the ceil function. Then we have maximum keys per node. Each node can have at most m minus 1 keys. So if we come back here, you saw this is a tree which is of order m, which is equal to 5. The maximum number of keys it has is 4. So m minus 1 is equal to 4 here. This is the maximum number of keys this tree can hold per node. Similar to that, we have minimum keys per node as well. So each internal node must have at least m by 2 minus m keys. So m by 2 is again 3 minus 1 is because this here also we have the ceil function. So this is 3 minus 1 is equal to 2. So each node must have a minimum of 2 keys when for a tree of order 5. Now it says except the root. Why the root is an exception? Assume that you have an empty tree at the moment. There is no other record, and you make your first entry. At this time, it has only one entry, that is one key, that is 10. The condition fails, right? This condition, m by 2 minus 1, it fails. So that is why the root node is comes under the exception tree. Okay, I mean exception as an exception. So it can have less than this these many number of nodes. It can have 0, it can have 1 also. So all the leaves are at the same level. The root can have as few as 2 children, or even 1 or 0 if it is also a leaf node. So in this case, this is the root and this is the leaf as well, right? So that's why it can have 10, I mean single node as well. Now let's start with the most important thing, that is insertion in B tree. If you understand this, insertion in B tree, okay? This please take a very I mean hear it with the attention. In all our examples, we will consider m is equal to 5. M is equal to 5. This is the order of the tree. The reason we are considering M5 is it is a perfect example of not very complex and not very simple. So if you understand this, you will be able to build the complexer examples as well. So based on the formulas that we calculated now, minimum number of keys per node will be 5 by 2 minus 1. This is 3, right? Then we have minimum children. Children is 5 by 2 is equal to 3. Oh, sorry, this is 2. I'm sorry. 2. Okay, great. What else? Is there any other formula that we need to consider? Maximum keys per node. Maximum keys per node also, right? That will be 4. So maximum keys per node will be 4. Now let's start with our example. Let's say we have an empty tree at the moment, and I will represent each node as an array because it is easier to represent. Okay, this is a root node. Let's start here. Okay, now let's say we insert 10. So 10 will come here, no problem. Now let's say we insert 40. 40 will come here, no problem. We are still satisfying our condition. Now let's say I insert 5. 5 cannot be inserted here, right? 5 will go here because it is always stored in a sorted way, correct? Lastly, let's insert 100. So 100 can come here, correct? Let's make our tree again. This is 5, 10, 40, and 100. Now, if I insert any other node, let's say I insert 200 here, 200 comes here. But do you see anything wrong with it? The number of keys it has now is 5, which is wrong. 5 cannot come here. I mean, there cannot be 5 keys. This entry is invalid. In that case, what happens? So in this case, the central node, the middle node, it is moved up. So what do I mean by moved up? We create a new node with the central node, which is 40. All the left node of this will become left part. This is 5 and 10. And all the numbers bigger than this will become the part of right subtree, which is 100 and 200. So this is how it is that B tree is split. Is our condition satisfied? So the root node has what is this is now the root node. It can we know it can have less than the minimum number of nodes as well, right? So this is correct. We have 5 by 10 minimum number of nodes. We saw how much we have is we have 2. Is our condition satisfied? Our condition is satisfied here also and here also. Great, sorted. Now, what we will do, we'll insert another node. We'll insert, let's say 20, right? So when we doing an insertion now, we come to the 40. Is 20 less than 40? Is 20 less than 40? Condition true? Yes, we'll come here. We'll insert it here. Okay. Now again, let's insert 2. Same thing is 2 will be inserted here. Now let's insert finally another number, let's say 30. Now what will happen? 30 comes here. Is this valid? No, right? 30, a node cannot have 5 keys in this case. So this 30 is invalid. What will happen? We'll do the same thing again. We'll split it. How we will split? So the 10 will become the parent. All the trees less than 10 will be here, 2, 5, and all the trees greater than will be here, 20 and 30. Now we will make our tree back. So this is 40, our root node, and 40 ka right child, we have 100 and 200. Do you see anything wrong with it? So only the root node can have less than minimum number of children. Is this the root node? No, right? This is wrong. So when you split here in this case, when you split a node, you add it to the parent node. You just don't create a new node here. You add it to the parent node. So here in this case, this was a root node. There was no parent, right? So that's why we created a new parent node 40, and then we added the two children to it. But when we are splitting this node, there is already a parent here 40. So we will just add it there. So how it will look like? The node will look like this. So we have 10 and we have 40. This is the root node. Now all the children less than 10 will be here, 2 and 5. All the children greater than 10, 20 and 30 will now come here. A new node got formed, 20 and 30. And all the ones greater than 40 are there where they were earlier, 100 and 200. Is that clear? If I just want to quickly iterate again, when you are splitting any of the internal nodes, you create, it's not like you append the middle child to the parent of this node. So the parent of this node is 40, this one. So this is this parent is this, right? This is the parent. So you split from 10 and you append it in 40. So 10 and 40. Now whatever the children nodes were, you just append it accordingly wherever the right positions. So this is how our tree looks now. Great. Let's take another example. Now what happens if the maximum number of keys in the parents I have already reached? Let's take another example. So we have 10, we have 40. Let's say we have 100, and let's say we have 200. This is altogether another example, so don't mix it up, okay? Less than 10 will be here, between these two here, between these two here, and greater than 20 here. Great. Okay. Now let's take example of this case only. This is between 100 and 200. So all the nodes here will be between these two values and in a sorted way. Correct? Now I want to insert 150 here. I say insert 150. What will happen in this case? So here, when you insert 150, 10, it will be split in from between, or let me explain it just like this. Let's cancel it. Uh, yeah. So this is 101, 102, 103, 104, and 150. This is इसी का zoom view. Now this is unstable. This is overflowing. We call it overflow here. Okay. What we do, we split this child. We'll raise it. This will go in the what did I tell you earlier? This will go in the parent. So its parent is this. It will go in the parent in the right place. So the parent will become. So if I zoom out a little, you can see 10, 40, 100, and 200 were the parents. That will be 10, 40, 100, 103, and 200. Okay. So all the things between these two remain as such. But now what will happen? So between 40 to 100, we saw there were some set of nodes. Between 10, I mean 100 and 103. And some new nodes got formed, right? So this is 101 and 102. 103 went to the parent. Between 103 to 200, we have 104 and 150. Greater than 200, we have other nodes. Is it clear? Okay. Now, do you see anything wrong here? This is the root node, and this is also overflowing now, correct? The root node can have a minimum number of keys, but it should, at all the cases, satisfy the maximum number of keys also. There is no exception for it in that case. So what happens in then? We again split the root, like how we have been splitting so far. So 100 will become the new root. This is 100. 100 will become the new root. It will have two children. Left part is 10, right part is 40. This part is 103, and this part is 200. Okay. Now, what happens to the children? Nothing will happen. So between 10 and 40, what were the children? The children will remain same. Whatever the children were here will be the same. Whatever were here will be the same. Whatever were greater than 40 will be the same. And same goes for 100 and less. I mean, yeah. So whatever were less than between 100 and 103 will now be less than 103, right? No condition is failing. Our tree is stable. 101, 102. Between these two were 104 and 150. Again, no problem there. And between, I mean, greater than 200, we had another set. So not an issue there. But each will have a minimum of two because of it has to satisfy the stability condition. Hmm. I hope this is clear to you. So this is how we insert. We find the right location where we want to do the insertion. We insert it. If the tree is big overflowing, we split from the middle node. We take the middle node to the parent. Now, if the parent also overflows, we split the parent also. So this is a recursive process that happens, and at all point the tree remains stable. And you can see all the leaf nodes are at the same level. Leaf nodes are at the same level. So this was insertion. Now, if you have to do perform any kind of search, let's say you want to search for 150. Search 150. What we'll do, you'll come to the root. 150 is greater, 150 is greater than 100, right? You will come to this node. You'll see, is 150 less than 103? No. Is it between these two? Yes. So you will come to this child. Then you will see, and you know that each node is sorted. So you can simply perform binary search on each node, right? So this is how it works, the insertion operation and the search operation. Now, how is it better than B trees? I mean, sorry, our binary search tree. The number of operations that we are doing has reduced significantly, correct? So let's say if we want to build the same tree, this is our binary search tree, and if we want to build the same tree of B tree of the same values, how it will happen? So in that case, we'll start with 50, okay? That is our first node that will be insert. So we'll insert it 50. Then we have 20 and 80. So 20 will come on this side, 80 will come on this side. Let's take order of m is equal to 4 here, okay? For different example. So order of 4 will have max key is equal to m minus 1, that is 3. This has reached maximum. Now, let's say I want to insert 10. Can I insert 10 here? So if I insert 10 here, what will happen? This is overflowing. So what will happen? We'll split the middle wala part. So how we will split? And again, what will be the minimum number of keys also we have to see, right? So minimum keys is equal to floor of, 2, C log m by 2 minus 1, that is 1. Okay. We'll split. So middle node is 50. So 50, we create a new tree. On the left hand side, we have 10 and 20. On the right hand side, we have 80. Correct? Now what do we want to insert next? Now I want to insert 5. So 5 can come here, not a problem. I want to insert 15. Where will 15 go? 15 should come here. But if we insert it here, what will happen? Overflow again, right? So what this node looks like now, if I want to insert 15, 5, 10, 15. 20. Correct? Now this is overflow. I cannot insert it here. What will happen? You have to split. This is the splitting point. It will split and go to the parent node. So how it will look like now? So it will look like, let's do it here. So it will look like 15 here and 50 here. Now, less than 15 is when you, sorry, yeah, when you split in, so for a clear view, let's do it like this. When you split it 15, you form again two portions, 5 and 10 and 20, correct? Now, how it will be split? So less than 15 is 5 and 10. Greater than 15 is 20. So it will come here, 20. And we already had greater than 50 is 80. So it will look like this. Is any condition being broken here? No. It can have single node because the minimum number of keys for m is equal to 4. I mean, the order of the D which with m order 4 is 1. So not an issue. Everything good. Okay. What to insert next? We have 60. Did we insert 40 already? No, we did not. Let's insert 40. Where will 40 go? 15. Is 40 greater than 15? Yes. Is 40 less than 50? Yes. So it will come somewhere in between. So here it will come. Correct? 40 will come here. Then we have 80. Okay. 80 already we have inserted. Next is 60. Is 60 greater than 50? Yes, simple, right? So we can simply add 60 here. So let me erase this. Yeah. So this will be 60 and 80. Clear? What is next? We have 55, 70, and 100 remaining. We note it down here. 55, 70, and 100 remaining. It was 70 only, right? Yeah. Okay. So let's get back. So 55. Again, it is greater than 50. It will go here. So I will have to erase this again. Okay. So this is 55, 60, and 80. 55 done. 70. Where will 70 go? It is greater than here. It will be inserted somewhere here. And this will again, this is overflowing. So what is a proper look for this? 70. When you enter 70 here, it will be split, right? Because the number of nodes are greater than maximum. The two halves are 55 and 60, less than 70, and 80. Now this 70 will go where? To the parent. How will the parent look like now? 15, 50, and 70. Now less than 15, we have 5 and 10. Between these two, we have 20 and 40. Between 50 and 70, uh, what did we have? Nothing we had because this is a newly created, right? So less than 70 will be between these two. So it will come here, 55 and 60, and greater than 70 will be here, correct? Lastly, we have to insert 100. Where will 100 go? Simple, it will be appended here, right? Now let's see the difference. So this is our the final tree that we formed in case of B tree. And here, this was the binary search tree. You see the level. So this was level 0, 1, 2, 3, 3 level. And this is just two levels. And if you change the value of m, that the level can go up and down, right? When you want to search for a value, you have to perform binary search here, and then directly you have to perform one binary search here, and one you have to move to that node and perform another binary search there. So let's say I want to search for 40. I will know one operation is here, second operation is moving to this node, and third operation is finding 40. So three operations it took. What about in this case? I want to find 40. So come to 50, one operation, two operation, and three operations. So in this example, it took the number of operations was same. So let's take another example. Let's try to find 70. Okay, let's see how it goes. So 70, yeah, here we find it in the first operation only. It is because it is in the root. But here, I came here 50, I came 80, then 60, then I found 70, right? Let's do a 55 also. Is 55 there in the root? No, no, 55 is not there in the root. Here, if you try to search for 55, the number of operations will be 1, 2, 3 again, right? And then finding, yeah, 1, 2, 3, 55, right? Here, in this case, we came to here, we we jump one operation here, and then 55 is found in the next level itself. So that's how so this is very basic example. Now imagine databases. The prime example of B trees, the prime usage of B trees is in databases, where the number of records are in millions. Just imagine how optimized or how better performing it becomes as compared to a binary search tree. This is why it was implemented. Now, so we have already seen the search operation, we have seen the insertion operation, the main operation, and probably the most complicated. I won't say complicated, but yeah, you need more attention to understand is a deletion operation. Deletion we can cover in a separate video. You can find the link to that in the description. Thank you for watching. Hope you learned something new.